Okay, so like I said, the last couple of lectures have focused on the reactions of radicals. And radical reactions have time and time again been shown to be particularly useful in organic synthesis, and have allowed for some, I think, the coolest transformations and cascade reactions. And so we're going to be talking about the fundamentals of radical reactivity today, and then we'll be doing some midterm practice afterward. So we didn't really talk too much about the specific reactions of radicals yet, but we have talked a lot about their fundamental characteristics, and how radical reactions work. And so the first big thing we talked about in radical reactions is this idea of bond dissociation energy. And in general, the bond dissociation energy is an enthalpic value that refers to the energy required, or the heat required to break a bond in a homolytic fashion. And what we mean by homolytic, we mean, for example, when we think about iodine, bond breaking in a homolytic fashion means that one electron from the bond goes to each of the two of the bonding partners. And so characteristic of radical reactions and important to radical reactions is that we draw our arrows for them a little differently. We use these fish-hooked arrows instead of traditional two-headed arrows. And so this represents the homolytic cleavage to form two radical species. Now, traditionally, of course, what we've learned in the past is heterolytic cleavage, which I'll show for comparison below with this two-headed arrow, which would lead to an iodide anion, an iodine cation. So heterolytic bond cleavages refer to the movement of two electrons, and when we discuss radical chemistry, we're thinking about homolytic bond cleavages, which is the movement of just one electron in each direction. And so the delta H of this reaction shown here is the bond dissociation energy, and it's, in this case, 36 kilocalories per mole. So for radical reactions, an important factor is bond dissociation energy, because radical reactions tend to involve the breaking of weak bonds. And so we can also show the heterolytic cleavage of the OH bond in water, or the homolytic cleavage of the OH bond in water, to form this hydroxy radical and the hydrogen radical. And in this case, the BDE is 119 kilocalories per mole. And so what we see is a very, this is nearly 80, or it's 80, so, or 83 kilocalories per mole difference in the bond association energy. And so what we'll say is that this iodine-iodine bond is a very weak bond, and this OH bond is a very strong bond. And so it's much more likely for us to be able to break weak bonds in a homolytic fashion than it is for us to be able to break strong bonds in a homolytic fashion. And we can really take advantage of this in synthetic chemistry into doing radical reactions. And so some examples of weak bonds are as follows. So classic weak bonds, halide-halide bonds, so X bonds, very weak. Chlorine, bromine, iodine, kind of fluorine, all quite weak bonds. And so we'll group them in the weak bond category. It's true also that other heteroatom bonds are quite weak. For example, the OO bond in peroxide is very weak. And importantly, carbon halide bonds, carbon bromine, carbon iodine, carbon chlorine bonds are quite weak, and we'll take advantage of that in chemistry. And so there's also what we'll think about as strong bonds. And strong bonds are those like XH bonds. So HBr, HCl, HI are all quite strong bonds, which is important because the XX partner is quite weak. We'll say that in general, carbon-hydrogen bonds are quite strong. Carbon-carbon bonds are quite strong. And we'll note that the CH bonds of alkynes and alkenes are strong as well. And also in this XH category, OH bonds, like we saw above, are quite strong, and as well as NH bonds. And then there's some that are kind of medium in their bond strength, and so we'll list them out. And those are things where the radical is stabilized in some sort of form, and we'll talk about this more on the next slide. But this is the aldehyde CH bond, the allylic CH bond, and the benzylic CH bond are all pretty weak, but relative. You know, they're stronger than the weak bonds shown here, but they're definitely weaker than the strong bonds. So I'll call them medium bonds. And so this is really important because radical reactions, the way they work and the way they propagate is that we'll break weak bonds and form strong bonds. And we can break strong bonds if it's paired to the making of other strong bonds. And so, for example, in CH brominations, the bromine-bromine bond can be broken quite readily because it's a weak bond, and that generates bromine radicals. Now, if we have, for example, this tertiary methyl radical, it's very unlikely, because this is a strong bond, for it to break like this, right? We think that process is unlikely because the bond association energy is too high. It requires too much energy to break that bond. But what is possible is if we pair it with the forming of a strong bond. So for example, that bromine radical that we formed by breaking a weak bond can react with this tertiary hydrogen to form an alkyl radical, an HBr. And like we said over here, XH bonds are strong. And so we can pair the breaking of a strong bond with the forming of a strong bond. And this allows us to access alkyl radicals and things that also that would require us to break strong bonds. We can do that by pairing it with the making of strong bonds. And so this is a very important fundamental process in radical reactions that makes them quite useful. And now we can access things like these alkyl radicals, which have a lot of synthetic utility, as we'll discuss further, and especially I think in tomorrow's lecture. Is there any questions on bond dissociation energies and how they affect radical reactivity? Okay, and so the next thing we talked about is that we want to talk about is some trends in radical reactivity. And the way you should think about radical species is that they're electron deficient. They're not a closed shell molecule. They're lacking one electron. And so in that way, you think of them as electron deficient species, right? And so things that stabilize electron deficient species also stabilize radicals. So if you thought about carbocation stability, it's also quite similar to radical stability. And so for that reason, for example, we know that tertiary carbocations are more stable are more stable than secondary carbocations, which are more stable than primary carbocations. In a very similar fashion, radical stability for tertiary radicals are more stable than secondary radicals, which are more stable than primary radicals. Now, when we think about bond dissociation energies, it goes in the opposite order because that's the energy required to form the radical. So if you're forming a more stable species, the bond dissociation energy is lower. And so for BDE, you just think about it as the opposite order as the stability. This is, of course, this is because the extra substituents can donate electron density toward this electron deficient center by hyperconjugation and induction of the CH bonds in these more substituted molecules. But another trend is also going to hold for hybridization. And so we'll say, for example, that in terms of stability, once again, stability, the CH or the alkyl radical from an alkyne is, sorry, actually this is in the opposite order, is less stable than the alkenyl radical, which is less stable than the alkyl radical. And so why is this? Classically, we can think about this as a hybridization argument. So this is this radical lies in an sp3 orbital. It adopts an sp2-like conformation, but it's really an sp3 orbital that inverts rapidly. This is an sp2 orbital, and this is an sp. And so a hybridization argument here for their stability is that with increasing s character, the electrons in those orbitals lie closer to the nucleus, right? Because the s orbital is around the nucleus. And that means that the more s character you have, the more electronegative it is, because it's closer to it's closer to the nucleus, which is where the drawing of electron density happens, right? This is where the protons are, and so the electron deficient species wants to be in orbitals that have more p character, that are farther from the nucleus. Similar to how you think carbocations, stability also trends with hybridization. The one difference, I would say, from carbocation stability is that radicals are always stabilized by resonance. And so in the case of electron withdrawing groups, we know that carbocations next to electron withdrawing groups are very unstable. However, radicals next to electron withdrawing groups that can delocalize them through resonance are relatively quite stable. We'll say radical species are never very stable, but we'll say more stable. And the reason for that is the following resonance structures that you can't draw for carbocations, where we can push the radical up into oxygen. Forget the 2 lone pairs on oxygen, and so now it has 7 electrons up there. And so because of this, these resonance structures available to this radical, it's a stabilizing effect. Notably also is the presence of electron hop stabilization of radicals. And so a good example of that is the alpha hydroxy radical. So if we had, for example, this OH bond, we can now hop a radical from the hydroxy group to this closed cell, or to this open shell species. So this is a resonance structure where we're just moving one electron, and that forms an anion here, as well as the radical cation of oxygen. And just for formal charge's sake, if we count the electrons around oxygen, it has 1, 2, 3, and then 1 from each of its bonds, so that's 5. And then we know its number on the periodic table is 6, and so it has a positive formal charge. And so this resonance structure does exist, and so stabilizes radicals next to lone pairs. And so radicals can be stabilized by a variety of resonance structures, but ultimately resonance is therefore always stabilizing for radicals. And so someone asked me if can we draw a similar resonance structure for the carbocation and push positive charge onto oxygen. Of course you can push positive charge onto oxygen, but this is disfavored because oxygen is quite an electronegative atom. And so that resonance structure is pretty much a negligible contributor. So just for highlighting this, doesn't this resonance structure exist? And I suppose you're right, it does exist, but it is negligible due to the electronegativity of oxygen, and so we don't consider it really a valid resonance structure. And so it does not significantly stabilize the alpha carbocation as much as the inductive effect destabilizes it. Right? Electron density gets pulled away from that carbocation. In the case of radical resonance structures here, the inductive effect is present, but this resonance effect is much more present, and so it's a net stabilizing factor. So those two things are always at play, right? Electron withdrawal from the electron withdrawing group through induction, but also resonance stabilization. Both of them are active, and in the case of radicals, it's a stabilizing effect. In the case of carbocations, it's a destabilizing effect. Because of their relative contributions. Are there any more questions on this? So to go back, but what makes XH considered a strong bond? Isn't it characteristic of a strong acid that associates readily from the XH bond? Yeah, actually, Dave, that's a great question, and is a little bit tricky to think about. So for example, if we consider HCl, which I've told you for homolytic bond association is a strong bond, but we know that heterolytically this association happens very readily to form H plus and Cl minus. We have to recognize that that's a different process than the homolytic bond cleavage. So to make H dot and Cl dot, we have to recognize that these species here are different, right? The chloride anion is different than the chlorine radical and has a different energy associated with it. And so while HX bonds are quite acidic, right? They're acidic. And in this equilibrium between these two, way far to the right on the acid-base equilibrium, they are also strong bonds when considering the homolytic bond cleavage. And so that makes them different. So there, you think of them as acidic but strong bonds when you consider radicals. And yeah, the two processes are separate. Don't strong acids only dissociate readily in aqueous solutions? Would these radical reactions occur in solution? So aqueous, strong acids dissociate well in aqueous conditions, but they can also dissociate in other polar conditions and react very readily with any sort of base. But these, especially BDE values, are calculated in the gas phase, and so are kind of irrespective of solution state. And a lot of times you can also calculate acidity in the gas phase irrespective of any solution effects. And you'll find in gas phase even HCl is a very strong acid, but it's still a strong bond toward homolytic cleavage. And so these have to do really with the relative stabilities of the chloride anion versus the chloride radical. Yeah. And so radical reactions can occur very readily in a wide variety of solvents. Yeah. Okay. If there's no more questions, we'll talk about the fundamental reaction steps in a radical reaction process. So in general, when we do and think about radical reactions, they can be, broadly speaking, divided into 3 steps. And the first step is always initiation. And so initiation is, we can recognize as the first step to form radicals, why it's given the name initiation, but can also, when we're using our chemical intuition to recognize what the process is, we should recognize that initiation always, or almost always, involves the breaking of a weak bond. So we listed out weak bonds earlier, and initiation involves the breaking of weak bonds. And so a classic initiation could be if you take bromine and you shine light at it, the energy of a photon is enough to overcome the barrier for homolytic bond dissociation. So this bond breaks, and we see this as a weak bond, and you form bromide radicals. And so this is possible because bromine is such a weak bond. You can't shine light at a CH bond and have it break because CH bonds are strong, right? You can't shine light at water and have it make hydroxy radicals because those bonds are so strong. But if we have a weak bond, we can initiate it with either light or with heat. And so classic initiators, which are really a dead giveaway for radical conditions, are bromine and light. So a halide, dihalide and light is a classic example. You can also have this reagent here, which is NBS, or N-bromosuccinimide. It's a nitrogen. So this is NBS. And the bond association energy of the nitrogen bromide bond is 46. So this is quite a weak bond, as hetero-atom bonds tend to be very weak. And so if you see NBS and you see NBS in light or NBS in heat, you should start thinking to yourself, this is probably a radical reaction. Also, if you see this here, benzoyl peroxide, the OO bond in benzoyl peroxide has a BDE around 30. So you should also be thinking to yourself, if you see benzoyl peroxide, radical conditions, right? Just upon heating, benzoyl peroxide will break this CO double bond, and then you'll get a decarboxylation to form phenyl radicals. And then another classic one is AIBN, which looks like this. Isobutyryl nitrile, AIBN. And just upon heating, what will happen in AIBN is this CN bond will homolyze, and that gives you nitrogen gas, which bubbles out and is the driving force for this, and two of these alpha nitrile radicals. And so this would be the active radical species. And so these are really three classic methods of initiation for radical reactions. And I would definitely commit these to memory, because if you see them in a synthesis problem, you should know right away that you're dealing with radical territory. And for when you're designing your own syntheses, these are classic ways to initiate radical reactions. Okay, so initiation is the what is the advantage of MBS over bromine? Well, you're forming necessarily a different radical. You're forming bromide radical and phthalimide radical, which have slightly different properties, but also it's most, I would say it's most oftentimes a practical reason. You don't want to shine light on every reaction, and so MBS can be done with heat, and also MBS is a nice white powder, where bromine is a volatile liquid, and so you know, I don't like working with bromine. It gets everywhere. MBS is a nice solid that you can weigh out. Yeah, so Tyler asked a great question, and he said, you know, so we can't break strong bonds photochemically, but can they be broken by simply reducing the wavelength of incoming photons? Yes. So that is a good point. If you made your photon higher and higher in energy, could you eventually break strong bonds with it? Yes. But that's not synthetically useful anymore, because you're also breaking all the strong bonds of the solvent. You're also breaking, you're homolyzing every CH bond, which cannot really be of synthetic use. And so for the wavelengths that we want to use in a chemistry lab, we can only break weak bonds with, and that is to our that's to our advantage. Okay, and so the initiation step involves the breaking of a weak bond to generate our radicals, and then in this reaction, what I want to do is I want to take this tributyl CH bond, react it with Br2 and light, and get bromination. And so what I'll be doing, what happens next is the propagation step. First step is initiation. Step 2 is propagation. So propagation involves the essentially all the steps in propagation start with a radical and end with a radical, right? So no radicals are, there's no net generation of radicals, and there's no net loss of radicals. The number of radicals in propagation steps always stay the same. And so, for example, the propagation step in this cycle is going to be the reaction of the bromide radical that we formed in step 1 with the CH bond. It does a CH abstraction to generate an alkyl radical, an HBr. This is the example where we paired the formation of a strong bond with the breaking of a strong bond. and the number of radicals here stays the same, right? So this is propagation because we had one radical and now we still have one radical. Another propagation step would look like this, where our alkyl radical reacts with bromine to give us the C-brominated product and the bromine radical. And here, once again, this is a propagation step because the number of radicals in the reaction stays the same. And so we go from having one radical species to having one radical species. It's a propagation event. And we'll note here that this propagation event actually delivers the product or our desired product for the transformation. Now, the third step of radical reactions is the one you oftentimes for productive reactivity want to avoid, and that's termination. And so in termination, you have the reaction of two radical species that form a closed shell species. So you go from having radicals to not having radicals anymore. And for our radical reactions, this is obviously deleterious because we want radicals to do reactions. And so if you're stopping the radicals, they can't react anymore. And so an example of a termination reaction here would be a combination of the tertiary alkyl radical with the bromine radical to give the product. Now, this delivered our product, but it stopped the chain. And so this is a useful termination reaction, but ultimately would slow down reaction overall. Another termination reaction could be the combination of two bromine radicals. To form bromine. Once again, this is not so bad because this is just our starting material, right? So this will absorb another photon and re-enter the cycle, but is a termination reaction because we go from having two radicals to zero radicals. And then probably the worst termination reaction for the purposes of reactivity would be the capture of two alkyl radicals to form this. Now, in designing radical reactions, part of the nuance is that radicals are typically formed in very low concentrations. So as we shine light on this reaction, we choose transmittance or a wavelength that can give us the desired breaking of bond, but we don't want it to happen so fast, right? And so that keeps the concentration of radical species low in concentration at any given time and can lower the chances of a termination pathway. For example, because the concentration of alkyl radicals in solution, concentration of these species is very low. And so the chance statistically for the two of them to meet is also very low. And so the rate of this termination reaction should be quite slow. Different to that is while the concentration of alkyl radicals in this case is quite low, the concentration of bromine should be high. And that will mean that the rate for this reaction is relatively fast. Same with this reaction. The concentration of bromine radicals is low, but the concentration of your CH bond of interest is very high, and so this is fast. And so relative concentration effects can help us favor propagation over termination. But ultimately, these are the three elementary steps that help drive forward radical reactions and is how we use them to do reactions. Is there any questions on this? Cool. No reactions. We will move on to the last thing we discussed in class, which is we didn't call this by name, but has been referred to by many people as the so-called reactivity selectivity principle. This is a pretty nuanced point of discussion, so I do want to spend some time with it because I think it has some implications when we think about reactions, and is, I think, of fundamental interest when doing organic chemistry. It's less useful for problem solving maybe, but I think is an important concept. And so we talked about this in class. We featured the reaction of propane with chlorine and light, which gives these two products shown here in a 60% yield and 40% yield, or ratio really. And propane with bromine and light gives solely this product here. And so we'll recognize that these products come from these corresponding alkyl radicals, right? Either this alkyl radical or the primary alkyl radical. And like we said before, the secondary alkyl radical is more stable than the primary alkyl radical. So why is it that we see some amount of primary CH chlorination? This can be explained. So if we think about this as the reaction of chlorine radical with either of these two CH bonds to form this radical or this radical and HCl, what we find for these processes is that these reactions are exergonic. They're negative in their free energy values. And so that corresponds to a energy diagram that looks like this, right? Where these are on the left and these are on the right. And so for the formation of HCl and this type of abstraction, this is an exergonic process. Well, it turns out that for the formation of hydrogen bromide and the formation of these two alkyl radicals, no product, we'll say that this one is likely not formed because we don't see a product corresponding to it, but it could be a possibility. What we see is actually that this process is slightly endergonic. And so the energy diagram looks like this. And so this is oftentimes used to explain the difference in selectivity, right? The difference in reactivity here. We'll say that the chlorine radical here is more reactive because it's a more exergonic process than the bromine radical, which is less reactive. There's oftentimes a correlation between reactivity and selectivity, right? The chlorine radical is more reactive and less selective, and the bromine radical is less reactive and more selective, and therefore we get the so-called reactivity-selectivity principle. Now, an explanation for the reactivity-selectivity principle has been put forth as the Hammond postulate. So this is the Hammond postulate, which is, I can summarize as saying, the transition state of a reaction looks like the reactant, if exergonic, and like product if delta G is positive. And so what does that really mean? And it actually, when we draw transition states like this, we normally draw the transition state, we normally draw the transition state right in between the starting material and product, but in reality, according to the Hammond postulate, it actually lies somewhere in between them and not directly in the middle. And so for exergonic processes like this, the transition state, or a more accurate energy diagram, might look like this, where the transition state, in terms of the reaction coordinate, looks more similar or is earlier to the starting material. So it looks like the starting materials. The transition state has more character. Of the bonds being broken and being formed, the transition state looks more like this side of the equation. And in this side of the equation, the difference in energy of these two CH bonds is very little. In the case of an energonic reaction, the transition state lies closer to the product. And so the transition state has character that looks more like the character of the products. And so when we look at the products of this reaction, we see we have a secondary radical and a primary radical. And we know that the secondary radical is more stable. And so the transition state energy for the secondary radical is going to be lower than the transition state energy for the primary radical. And so maybe this is more easily shown if you think about there's two transition states, right? One that leads to secondary radical formation and one that leads to primary radical formation. And so I'll draw a second, or I'll change the color of the secondary radical. And we'll put it onto our diagrams. And so because there's an early transition state for this reaction, the two transition states are very similar in energy because they look the same in the starting material. Because there is a very late transition state in the second reaction, the energy of the secondary alkyl radical is very different than that of the primary alkyl radical. And so the two energies of the transition state are very different. And so in this case, the secondary alkyl radical is lower in energy. And so we'd expect it to have a lower energy transition state. And so that the ability of the bromine radical to traverse this lower energy transition state gives a selective formation of the secondary alkyl radical, where in the case of the chlorine radical, the two energies of the transition states are very close to each other because it's early. And therefore, there's not a lot of selectivity. So that is, in turn, with the Hammond postulate, we can explain this selectivity-reactivity principle. I got a question that said, can you explain why the reaction with chlorine is exothermic? I know the HCl bond that's formed is strong, but isn't the alkyl radical a lot less stable than the chlorine radical? Yeah, so this is just when we think about bond strengths. So actually, I don't have the number for the BDE of HCl written down, but the HCl bond is stronger than the carbon-hydrogen bond. And so this reaction is exothermic. I think it's like nearly like, so alkyl CH bonds are like mid 90. I do believe that this is around 100 kilocalories per mole. And so it is, we're forming a stronger bond than we're breaking. And in the case of the HBr bond, the HBr bond is slightly weaker than the CH bond. And so that reaction is endergonic. And that's why they get the one's exergonic, one's endergonic, is because the relative strength of the hydrogen chloride and the hydrogen bromide bond. The hydrogen chloride bond is stronger than the hydrogen bromide bond. Any other questions? The reactivity selectivity principle is certainly very important, and so is the Hammond postulate. And if any of you go on to take the physical organic chemistry class offered as an upper course elective, which I think you all should because it's awesome, you'll talk about these things in a lot more detail. I just thought I would break some ground on it for you. Okay. If there's no more questions on this, then we'll break into our problem-solving portion of the day. And so here are some examples for mechanism and synthesis practice. And so these come from some of the later work we've been doing in synthesis. So I would, I recommend you try these reactions and the reaction mechanisms too, without your notes first, so you get really familiar with them, and then of course go back and use your notes. So let's try and work on all these problems, and we'll come back in like 15 minutes or so and discuss them. This last one is a synthesis, so propose a synthesis that goes from here to here. Okay, so let's break for 15 or so minutes, and then we'll talk about these. Okay, so we've had some 15 minutes to work on these. And so let's start to talk about each of them in turn. I think that the thing I was trying to get away from these reactions is to start having you think about the synthetic utility of the alkene cleavage reactions that we talked about in lecture a few weeks ago. The first of which is in problem number 1 is the ozonolysis reaction. And so we know that that the ozonolysis reaction can take alkenes and react them to cleave the carbon-carbon bond, and in the presence of a reductant, lead to the formation of aldehyde products. And so this should be the structure of A, and then treatment of this compound under potassium tetroxide conditions should form the corresponding enolate from our aldehyde. Which can now, like we learned for the last exam, undergo an aldol reaction. This would form a 5-membered ring, right? 1, 2, 3, 4, 5. Then we'd expect for another deprotonation to form another enolate. Now this can form another enolate, which can eliminate the hydroxy group in an E1CB fashion to give this aldol condensation product. Shown here. And so real synthetic utility here of the ozonolysis reaction is the ability that we were able to traverse from the 6-membered ring now to the 5-membered ring. And so we can get to a pretty topologically different product here. Any questions for this reaction? Okay. So the next reaction is another example of a alkene cleavage sequence. And so we'll talk about the synthesis of this fragment in just 1 second. But we learned in class that the reaction of osmium tetroxide with alkenes happens quite readily, and this leads to the dihydroxylation of alkenes. in, ooh, that was awful, in a syn fashion. So it either looks like this or the enantiomer of this. So now this, when treated with, this is A. When treated with sodium periodate, we know that this will also undergo an alkene cleavage reaction. Oops. To form also the corresponding aldehydes. And then so this is the product after the first step. And now we can recognize these conditions here as those for the reductive amination of aldehydes. And so just a reminder what that looks like. You have R, and this undergoes the condensation of an amine. We'll say the amine here is the same. You get to an iminium species. Which is then reduced by sodium cyanoborohydride. This is a hydride reducing agent. So you can think about this as just an H- source. Similar to the reductions with sodium borohydride that we talked about for the very first exam, to give you the reduced amine products. And so we have two aldehydes here, and so the products could look like I think there's also probably in this some opportunities to think about some other potential products, but I think this is a very reasonable one. And so this required some recall of the hydride reduction reactions that we talked about for the very first exam. So a reminder that everything in organic chemistry is cumulative, and so especially when it comes to synthesis, right? So be sure that you're aware of the different transformations that we've learned this semester, so that you can apply them when thinking about synthesis. So that also leads to the question, how would you make this with fragments of 6 carbons or less? And when you see an indole, you should really think about the Fischer-Indole synthesis reaction. And so that very generically looks like R plus so it's a reaction of carbonyls with phenyl or with hydrazines, specifically phenylhydrazines. And that forms indoles. And so when you see, so this is Fischer indole synthesis. So when you see indole fragments, you should always think Fischer indole synthesis. And so if I were to pull out the two fragments for this, I would say, okay, I made this by Fischer indole synthesis. And so I take phenylhydrazine, and I would also plug in this to this. And so I would plug in a carbonyl that looks like this. So cyclohexanone, cyclohexenone. Does this make sense to everybody? So a real clear understanding of how to make indoles, and the best way to do that is often Fischer indole synthesis. Okay, seems to be good. I'm gonna do some erasing. Okay. So someone asked, how do I know that the double bond is going to end up on the right side? So if we map, well, let's go. That's a great question that can be explained by the mechanism of Fischer indole synthesis. So let's do the mechanism of Fischer indole synthesis. The first step is condensation. So the hydrazine will condense onto the carbonyl. So we get this hydrazone. Here. We get a hydrazone. And then the next step is tautomerization of the hydrazone to its enamine form. So we'll shift this alkene here. And a 3,3 sigmatropic rearrangement. To give this this structure. Shown here. And so now you see we made the carbon-carbon bond, that is this carbon-carbon bond. And so it makes it to this side because that's the one with an available proton to make the enamine that undergoes the sigmatropic rearrangement. And so we'll follow this through first we'll get re-aromatization of the phenyl group. So that's just an elimination and protonation. just essentially a tautomerization again. And then this amine will condense onto the imine, will lose ammonia through condensation and form product. And so I hope it's clear to you that the alkene ends up on this side because there is no proton here to make the corresponding enamine. Cool. Okay. And so for this bottom problem, it's a synthesis problem. Does anyone have a suggestion on a synthesis? Okay, well, if there's no suggestions, then let's think about the synthesis problem. So we see we have one, two, three carbons here. I'm going to at least make an assumption for the sake of problem solving that perhaps this hydroxy group is this hydroxy group, but maybe that's not a good assumption. We'll see. And so in our product, we see that we have added a phenyl group, and there's now one, two, three, 4 carbons. And so we're going to have to either add a carbon, we could add 2 carbons, lose a carbon. There's a lot of variance here. And so there's a lot of things that you could possibly do. And so one thing that I'm reminded of from what we learned in class is the Johnson orthoester synthesis. And so if you remember this, where'd my mouse go? Oh, there it is. We learned that treatment of allylic alcohols, homoallylic alcohols, there's one more space in between. No, it's allylic, sorry. Treatment of allylic alcohols with orthoformates led to products that look like this. And I'll abbreviate a mechanism here wherein an alcohol displaces one of these ethoxy groups, and that forms, or formally displaces one of the ethoxy groups, that forms an intermediate that looks like this. This isn't the only way to do this problem. I think there's probably many. Then we can think about the ejection of another ethoxy group. Formation of this oxocarbenium species. then tautomerization, to form this alkene, which can undergo a 3,3 sigma tropic rearrangement. Sorry. Yeah, no, that's right. To get us to here. And so now when I look at this, I have something at the ester oxidation level. And then 1, 2, 1, 2, 3 carbons to here. And so we also noticed that we added 2 carbons, right? We added 2 carbons. And so we're at something with a carbon chain of 1, 2, 3, 4, 5, and we want to get it down to 4. And so what I would suggest is an oxidative cleavage of this alkene. So if I did ozonolysis and DMS, that would give us corresponding aldehyde. And if I reacted this with a copper-derived phenyl nucleophile, I would expect this to add into the more electrophilic and available aldehyde. That adds our phenyl group. And notably, remember, cuprates aren't really nucleophilic enough to react with esters very well, and will preferentially react with the aldehyde, and then this can undergo cyclization and loss of ethoxide to give the product. So I think this is what 3 steps. It seems pretty reasonable. I'm sure there are probably some other answers here that I think are probably valid as well. But this is one that I came up with. Is there any questions on this? Okay, no questions, then we'll move on to my next set of practice problems on some cycle addition practice problems. And so I'll give you a little time to work through these problems as well. Okay, so in the interest of time, let's go over these. Give me just 1 second. I'm going to stop sharing my screen. Just one moment. Okay, sorry, let me share it again. Okay, and so for this first reaction, we want you to draw the endo and exo transition states that would lead to, you can see my PowerPoint screen? Great. That would lead to the endo and exo product, and then we'll talk about which one's more favorable. And so the way I'm always going to do this is I'm going to draw the transition states, or at least the approaches. And so we have this transition state here where we form these bonds. This is going to be the exo transition state because these groups are pointed out of the transition state. And so it gives a product that looks like this. Through this arrow pushing for the Diels-Alder reaction, gives a transition state, or it gives a product that looks like this. Which shows us that the bridge here is on the same side as the groups. So the exo product would look like this. So if the methylene bridge is up, we see also that the 5-membered ring is up. And the hydrogens are down. The endo product is going to arise from the endo transition state. So if we draw the alkene, the endo transition state has these groups pointed inward so as to allow for a secondary orbital interaction between these pi accepting carbonyl groups and the internal pi orbitals of the diene. And so that would give products that come from this transition state, where we still are forming these bonds. And so that gives a product that looks like this. Kind of the cramped drawing there, but you see now the bridge is on the same side as the hydrogens, and so now instead for the endo product, we see the opposite diastereomer. Now, of course, these are both formed as a mixture of enantiomers. So we'll give a plus minus here to show that the other enantiomer is also made. So typically we think about the endo product if it has these pi accepting groups on them, electron withdrawing groups or more alkenes or something along those lines, something with pi orbitals. We think we think of the endo product as being the kinetically favored product because of this interaction in the transition state between these two pi orbitals. And we think of the exo product as being the thermodynamic one because it's significantly less hindered when thinking about steric hindrance. And so these are the endo and exo products. Any questions on this one? I think this should be something that becomes very routine to you. You should get a lot of practice with it. Now, for this second example, there's two things at play here. Not only is there polarity of diene, as we see that in this case, the diene and dienophile were symmetrical. In this case, they're asymmetric. Or unsymmetrical. And so we have to think about polarity of the diene, and we also have to think about the relevant transition states. And so I'm going to rotate this diene into the S-cis configuration, which looks like this. Now we need to assess the polarity of the diene. So there is this lone pair here on oxygen, which can donate electrons into the system. And so we think about this resonance structure here. Which tells us that this terminus is the one bearing electron density. And so this is the delta minus side. We think about that resonance structure here in the dienophile, which gives us this, which tells us that the delta positive end of the dienophile is here. And so we're going to want to match delta negative to delta negative, to delta positive for the reaction. And so let me, knowing these things, which size we need to match, we're going to draw our diene in perspective. And we're going to draw our dienophile with the matching ends here. So and we're going to form these bonds. And now I've chosen this polarity because, like I said before, and I've chosen here the endo transition state, noting the fact that there are pi orbitals on this carbon, and so they're going to overlap well with the pi orbitals of the diene, and so the endo transition state will be preferred. And so we get this as the diastereomer transition state that we are looking for. And so let me draw, and I'll just draw the immediate product from that. the cyano group going in, methyl group coming out. Okay, and so what we see here is that the acetate and cyano groups are on the same face. The methyl groups are also on the same face, but they're on the opposite face as the other two. And so the major product here will look like so. As well as the other enantiomer. And so this will be the product form. The last example here is a dipolar cycloaddition. The same endo-exo selectivity rules apply. Notably, in these systems, side with oxygen is delta minus. So you could draw, yeah, so this is delta minus because oxygen has a negative charge. And this is delta, and this is once again delta positive. So we will get a matching of delta minus, it's just minus in this case, and delta positive. And so our product here will be a 5-membered ring. Like so. And so yeah, so it'll look like so. And so now we should evaluate the relative stereochemistry of the phenyl group and the cyano group. And so we can draw a transition state here. Once again, the endo product will be preferred. And so the initial product right after cyclization will be this, and we see that the phenyl group is on the same side as hydrogen, and so the stereochemistry here is anti. Air pushing here, oops. Looking like this. Okay, I hope that makes sense to all of you. Cycloaddition reactions are obviously going to be a big part of the exam on Thursday. So I want to ask for the second one, can you go over the stereochemistry for the methyl/acetate? Yeah. Well, which methyl? So I see here that the acetate is on the, so the acetate, these two hydrogens are on the same face, and that this hydrogen is on the same face as the methyl group. So hydrogen and methyl group must be on the same face. And so hydrogen is up and methyl group is up. And I see here that these two methyl groups are on the same face. And so methyl group must both be up. Does that make sense? I'm just going through the, I look at the relative stereochemistry in my product that results from the transition state, and I just assign it all based on that. Is the phenyl group on the nitrogen pointing in for the third one? The phenyl group, so we have to remember that nitrogen here has a lone pair. And so though the it's sp3 hybridized still, that lone pair rapidly, it goes for rapid tunneling through the nucleus. And so you get inversion of the stereochemistry there. And so it's not configurationally stable. And so nitrogen, in most cases, is not chiral. There's not chiral at nitrogen because that lone pair inversion happens so rapidly. So even though it's sp2, it's not really chiral. Sorry, even though it's sp3, it's not really chiral. Okay, if there's no more questions, I'll thank you all for coming tonight. And I will see you on Wednesday, where we'll have a big Q&A and some practice problems. So so please make sure to come prepared with any problems that you have. We'll really try and tackle them all on Wednesday, and then we'll do some problem solving. Would I be willing to post the slides? I might post the slides. It's just a little confusing because I did some stuff and erased some stuff, so they don't become super useful. But I will definitely post the recording so you can see everything. Cool. Have a good night, everybody.